Here we have another eigenvalue eigenvector problem where we're trying to find the eigenvalues and eigenvectors of a 3 by 3 matrix. One of the things to notice here is that this is not a symmetric matrix, so we cannot be assured that the eigenvalues will come out to be real or that the eigenvectors will be mutually perpendicular. But we'll begin this process the way we begin all of these. We're going to calculate the determinant taking lambda off each of the diagonal terms, and keeping the non-diagonal terms as they were, and we're going to be setting the determinant equal to 0. When we expand this out, we get 1 minus lambda times 3 minus lambda times 2 minus lambda. And then what are the other terms? You'll see that this diagonal in this direction involves 0 terms, so there's nothing there. And you'll also see that this diagonal, so all of the 3 positive diagonals, only one of them makes a contribution here. Now how about the negative diagonals? This diagonal has a 0, this diagonal has a 0, and this diagonal has a 0. So in fact there are no other terms to consider when calculating the determinant, so this is then just set equal to 0, which means not only if we could expand this out to get our characteristic equation, but since the problem didn't specifically ask for the characteristic equation, it means that we already know what our eigenvalues and our eigenvectors, we already know what the eigenvalues are. What are the eigenvalues? They're the roots here that's shown, and what are the 3 values of lambda that would make this equation be true? Lambda is equal to 3, or 2, or 1. So those are the eigenvalues. They're 3, 2, and 1. So all of those are eigenvalues. Next, we need to find the eigenvector associated with each of these eigenvalues. And so let's start with the first one. For lambda equals 3, we're going to take 3 off each of the diagonal terms. So we have 1 minus 3, and then our off diagonal term, minus 1, 0, 0. And then for the next row, we have 0, 3 minus 3, 0, 0. And our last row, we have 1, 0, and then 2 minus 3. Okay, when we write that out, or subtract those terms, we get minus 2, minus 1, 0, 0, 0, 3, minus 3, whoops, made a mistake here, 3 minus 3 is 0, 0, 0, and then 1, 0, minus 1, 0. Okay. We can go ahead and apply Gaussian elimination to this, and when we do that, we would take the first row and keep it the same, minus 2, minus 1, 0, 0, and we would take 1/2 of row 1, we'll keep row 2 as it is, and to get rid of the 1 at the start of row 3, we're going to take 1/2 of row 1 and add it to row 3 and put that sum here. So that first term is 0. 1/2 of row 1 is minus 1/2, minus 1/2. And then minus 1/2 times 0 plus a negative 1 is minus 1. So that's what we get. And from this, we can see from this last equation that minus 1/2 x2 is equal to x3, or x2 is equal to minus 2x3. And from equation 1, we get minus 2x1 equals x2, but we know that x2 is equal to set equal, we can substitute this one in here to get minus 2x1 is equal to minus 2x3, or x1 is equal to x3. So if we arbitrarily pick an x3 of 1, we would get, if we arbitrarily pick an x3 equal to 1, we would know that for x2 is equal to minus 2, and x1 is equal to 1. And that is the eigenvector for, that's the eigenvector for lambda equals 3. So far we've found one eigenvector associated with the first eigenvalue. Now let's look for the eigenvector associated with lambda equals 2. So for this one, we have the system of equations 1 minus 2 minus 1, minus 1, 0, 0. Then we have 0, 3, I should have written that down, for lambda equals 2. That's the eigenvector we're now solving for. The next term in this system is 3 minus lambda, or 3 minus 2, is 1, 0, 0, 0. And then in our last row we have 1, 0, 2 minus lambda, or 0, 0. From this last equation we know that x1 is equal to 0. And from this equation we know that x2 is equal to 0. And from this equation we happen to learn that x1 is equal to minus x2, but that's not telling us anything since we knew there were 0. We have no information on x3. In fact, what it's saying is that x3 is any number, and we'll just arbitrarily choose 1 to keep it simple. And we know that x1 and x2 are then going to be equal to 0 from those equations. So that's the eigenvector for lambda equals 2. And now we have one more eigenvector to solve for. So for lambda equals 1, we get the system of equations 1 minus lambda, or 0, minus 1, 0, 0. The next row we have 0, 3 minus lambda. And in our last row we get 1, 0, and then 2 minus lambda. 2 minus 1, or 1. From either of these two equations we get that x2 is equal to 0, and from this last equation we get that x1 is equal to minus x3. So if we arbitrarily pick x3 equal 1, we know that x2 is 0, and x1 is minus x3. And that's our eigenvector for lambda equal 1. And we found our third eigenvector for this the original matrix given in this problem.